Okay, hello. Hello. So, like to start the live stream. This is Junichiro Horikawa speaking, and this is the 98th episode for Houdini Algorithmic Live. It's a weekly tutorial live for Houdini, and the topic for this week is to create a 3D visualization of a so-called Calabi-Yau Manifolds, which is a term which you can find. Let me and look at the Wikipedia. Okay. So it's also known as Calabi-Yau space, a particular type of manifold which has properties such as Ricci, flatness, yielding application to theoretical physics. And this image that you see is a representation of the 66-dimensional Calabi-Yau sliced in 2D. And what I am going to create today is pretty much similar to this image. And in order to do that, we are going to follow the equations in order to visualize this in 3D. So since the original shape itself, original space itself is in 6th dimension, so we do need to, if we want to see it in 3 dimension, then we have to get the shadow of that image. And in order to do that, I have searched for how you could actually visualize it in 3D. And if you search for Calabi-Yau Manifold 3D, there is a website which shows a 3D representations in WebGL with these parameters, and kindly enough, it also shows a algorithm, like the equations in order to project the 6D image onto a 3D space by following those equations and using these code. In this case, it is written in JavaScript plus a 3.js library. So I am basically going to follow the steps that this guy has wrote in this blog, following how he has implemented the visualization in 3D for this Calabi-Yau manifold. Now, one thing I need to mention is that when you do the calculations, it is using the complex numbers when you look at the equations. For example, right here, for exponential calculations, you have this negative value here, or imaginary value here, like that. You also do need to calculate the trigonometry, cosine and sine, with the complex numbers like these. And what else? So most of the heavy calculations are done in this functions here, having exponential, and you also have power, which can be visualized or realized by using the exponential functions, which is somewhere right here, I guess. This one right here, phi. Not really. Where does this So you have this calculation here, exponential math complex, which stands right here. And also you have the trigonometry here. So one thing you need to do in Vex, one thing you need to know how to do if you want to do it in Houdini is how you can actually calculate the complex numbers. And I don't really want to use Python for this one because Python is a bit too slow to use it for the geometrical operations in Houdini. So most of the time I do want to use Vex. So what I need to know is how you can calculate complex numbers using Vex. Okay, so and the result, I'm just gonna show you the result first. The result that I'm gonna get here is these Calabi-Yau manifold shape in 3D. What you can change is exponential value as well as the projection angle for the shadow in 3D. And these are optional. I didn't just want it to finish by this. This is just too simple, so I wanted to experiment with the output, if what kind of things that I can do after I have created a surface. So one thing I have added is kind of a wavy pattern on top of the surface like that, which is pretty simple to do, but as an addition. Okay, so those are the results that I'm going to get for this tutorial. And most of the things that I'm going to show you today is how you could calculate complex numbers in Vex. And that's the main topic. Alright, so let's see. So I'm gonna start by creating a geometry node. And I'm also going to move this website to the side as a cheat sheet. Okay. So in order to implement this, you do need to know how to read the code. In this case, a JavaScript. But as you can see, this is really a short number of lines, so I think it's pretty much easy to follow. Let's see. So this is where you are calling the function called Calabi-Yau, which is this one right here. All right. And inside this functions, you are also calling the function called coordinate right here in order to change the 2D vector values into 3D, which is where that is. Oh yeah, this one here, right here. So this is a one function, and these are the process that is calling coordinate right here. And it is creating 4 sets of points and push it to the meshes array. And I think this means is that you are creating a quad plane for each. In this case, we have 3 loops, right? So inside this for three for loops, you are creating a bunch of quad planes with these coordinates converted into 3D right here, and make it as a mesh by combining all those planes together. All the other functions listed below are mostly about for the renderings, how to visualize it using custom materials, so we don't really need that. So only thing we need to care about is these stuff here. Now, one of the problem when you want to implement this in Houdini is that it is using tons of for loop, which is not really efficient at all. I mean, you could do that by using attribute wrangle and change it to a detail, then just use bunch of for loops inside the code to run pretty much the same code written right here. But that's gonna be too consuming too much process, I mean, computer process, when you want to change the parameters in real time. Okay, so instead of doing that, I would like to use one of the multi-threaded wrangle, maybe primitive, points, or vertices. Okay. Now, since we know that we are creating tons of quads for a number of loops, if we know the total number of quads in the last, then we could stop by creating the grid, then modify each quad using primitive wrangle and just change the point position of those quads. And I think that makes more sense when you want to do a fast processing implementation. Okay? Especially when if you want to do it in Houdini with the Bex, that's more efficient, I think. So let's try to do that. I'm just going to save this first. Call this Calabi-Yau. Alright. So let's start by creating a grid. And let's also look at the code. What kind of loops do we need to care? Since we do need to know how many quad planes we need to create, like how many squares we need for this implementation. So the first loop, it is using a d3.cross. D3 is another library for JavaScript, I think. And cross means it's creating a cross for loop, meaning if n is 2, then 2 by 2 loop. If n is 3 by 3 loops in this case. So n is one of the parameter we need to deal with, which if you look at this one, so n can be considered as a exponential numbers, which is this one, exponent number right here. This is n, and projection, this is an angle based value, is this a. So we're gonna follow this, and let's have that parameter stored in one of the controller, one of the null node, so that we can use it for many places. All right, let's have it right here. I'm just gonna name the parameter written as here. Exponent starting from 2 to, I don't know, any number, so 2 to 10. And a projection is an angle based value, which is based on radians. So let's give a float value, name it projection. Let's say from 0 to 10. Oops, where'd it go? 0 to 10, all right. So, and what else? We also do need to know the resolutions of the quad, like how many boxes, how many squares we need to have. And if we look at these code carefully, first value you see is these dx and dy. This is the iteration number for each loop inside this loop here, and which being used right here, dx and dy. And if you look at the second loop and the third loop here, see that the range is from 0 to pi divided by 2 and incremented by dx for this loop. And this one minus pi divided by 2 to pi divided by 2 and incremented by dy. So this actually is a number of by using these value dx, dy, and the range from 0 to pi divided by 2, you'll be able to get how many loops, how many iterations there are there for each loop, which also determine how many quads you have. Okay, so the first loop is n multiplied by n, and the second loop you can get the iterations by dividing math.pi divided by 2 divided by dx, and by doing that you get an integer value, how many loops, how many iterations for this loops, and do the same things for the third loop, and by multiplying all those numbers together, finally you get the number of quads. Okay, so in this case, for myself, I do want to define the resolution by myself. I don't want to hard code the resolutions like this, so I'm just going to create a resolution based, or let's say div division value, so that I can change the resolutions by myself using this slider. Okay, let's copy this value and first of all paste it into the rows and columns. Alright, now if I change this to something really small like 4, I do want to have 4 quads on the x direction and z direction, but right now I only have 3, so what I need to do is to add 1 to these parameter so that I get 4, the same number that I enter here for these quads. Okay. Now that's the first step. Now the next thing I would like to do is to create the copy of this quad multiple times. Okay, so this is currently corresponds to the loop for the second loop and the third loop. The second loop is for the width, the x directional loop, and the third loop corresponds to this loop here for the y direction, right? Now in this case you have a negative range here, but let's forget that for now, and I'm just going to use this setup for now, and I'm gonna come back to this negative range later. Now, so this quad itself represents the second and third loop, and the last loop that I need is these first loop. So in order to do that, I can just move the quad to the left or bottom, or I can just use something like duplicate to just copy the grid that I have right now with a number of exponent value by the same exponent value. So if it's 7, then you multiply 7 by 7, which is the number of duplicate you want to create for this quad. So connect it and copy the exponent, paste it right here, and let's use the power function with 2 so that you get 7 by 7, 49. All right. Okay, so let's go on with this, and I'm going to increase the resolutions a little bit, like that, 20 something. Now in total, right now I have 21,000 primitives. Okay, so what I want to do is to change each quad's point position based on this coordinate function right here. Okay, we're using, in this case, primitive wrangle. Since I'm going to process each primitive in one time, it's gonna be faster rather than using loops like this. Okay, so let's call this Calabi-Yau. So this is just going to be the main function to write, and if it's all done, then that's pretty much it. Okay, I'm going to open up the code editor and try to follow the step. Okay, now first of all, I'm going to bring up the parameters that I set here in the controller. Okay, so I have exponent, just gonna call this n like it says in this code. CHI. And I have this projection. I'm just gonna call this A. Alright, and I also have the division. Alright. Okay, and let's promote these parameters. Now, let's copy those parameters from controller to this wrangle. Like that. Okay, like that. All right. Oops. Okay. Now let's see. First, let's try to follow these, and later I'm gonna come back to implement this coordinate function. Okay, so so this indicates how many loops we need, but I already skipped that part, these part, by making the initial grid like these. All right, so we can start from somewhere around here. Now, let's see what I need to do here. Okay, first of all, we need this x value here, and let's see how we can get that value. Right, so in order to do that, what we need is these k, x, and y value, which indicates the value in between these ranges, like that. Okay, so let's try to get those values. So what we need to have is k. Actually, inside the k, this is a array which contains 2 items inside, first k value and second k value. So we need to have k1, k2, and we'd also need to have an x, and x plus dx. Now I'm just gonna call the x as x1 and x plus dx as x2, so since this is the next x value. Okay, and we also have y1 and y2, like that. So I think these are the value that I need to know in order to call the coordinate. So let's assume that I have the coordinate functions set. All right. Now, for a x value, d dot x means these arrays. So it is using another map functions right here. So we don't have a map functions in Vex. So instead of doing that, instead of writing like this, we need to write a for loop. And for the for loop, we are looking at the data array, which is this one. So let's try to create this array first. Just gonna copy it and change this to, since this looks like a vector 2 to me, I'm going to create a vector 2 array instead of dictionary. So replace some of the code and gonna replace it with set x1 y1. Okay, set, and this will become x2, and this is a y1. Rest the same. Set, this is x2, y2, x1, and y2. All right. Let's see. Okay, I got an error. Okay, unexpected identifier on 6. Okay. We don't have this function yet. Okay, bracket. All right. So we have this data, and in this code, it is mapping each d value to a 3D coordinate right here. So in order to implement that in Houdini, we are going to look at each data value inside the data array like this. And first of all, get the d value from each data from the array data like this. Now we have the same value d like this, so we can access d.x, d.y. So if we have the coordinate, we should write d.x, d.y, and we also have n here, and k1, k2, k1, k2, and a. Okay, so hopefully this will be this is going to be the function that I'm going to call. Okay, some errors. Okay, data. Let me see. Call to identify the array index operator 222. I think I'm doing something wrong. I should make it as a vector 2 array, right? Okay. So what's next? So what we need to know is how we decide these values right here. Okay. And I'm going to get these numbers, since each of the numbers coming from based on the iterations for loop, each for loops, first, second, and third. In this case, we already have a number of iterations shown as number of primitives. So what I'm going to use is the primitive number itself and convert it into these numbers. Okay. Now the primitive number is this, and somehow by calculating this value, we're going to change this to k1, k2, x1, x2, xy1, and y2. That's what I'm gonna do. All right. So how we do this? In order to do that, we need to we do know that the number on the x direction is equal to division, div number, right here. So let's just say 10 to make it simple. So we have 10 on x direction, we have y on 10 directions, and we have copy of 7 multiplied by 7. Okay, so by using those informations, we could get the x number for this grid, such as starting from 0, 0, 1, 2, 3, 4, 5, 6, 7 until 9. And we can also get the value in z direction from starting from 0, 0, 1, 2, 3, 4, 5 to the 9. And we can also get the informations for k1, k2 by using this 49 copy of this grid. Okay, so k1 could be 0 to 6, k2 could be again 0 to 6, and each of the plane number itself, the grid number itself, corresponds to the combination of k1 and k2. If k1 and k2 both are a 6 and 6, or a 7 and 7, is it? 6 and 6, yeah. 6 and 6, then it corresponds to the last grid number. Right. I'm not sure if that makes sense, but let's consider that in mind. Let's try to get each numbers. So the simplest value to get is the simplest value you can get out of the primitive number is by let me see. Now first of all, we do need to know the k1 and k2. So let's try to get that value, okay, for each primitive out of this primitive number. Okay, so in order to do that, let's see, let me think. So we have okay, so I'm going to start by creating a combination of k1 and k2. Let's call this k, which is in between 0 to 48, since that's going to be the total number of k1 and k2. So we have 49 like grids. So this k indicates the number of the grid itself. If we are seeing the number 0, then there's also 1, 2, 3, and 4 and on the back side having the same number of width and height. Okay, so how can we calculate the k value from the primitive number? Now, first of all, we're going to place the primitive number, and we are going to just calculate the remains using modulus by multiplying a division, multiply division, which is 49 in this case, since we have 49 grids, 49 we have 49 total number of grids. So this is the first No, actually I don't want to calculate the remains, but I just want to calculate the divisions, like that. Then as a result, you get a value in between 0 to 49, is it? Wait, is it? Let me see. Maybe not. Maybe not. This will be equal to... No, I think I'm correct. Sorry, division is not 49, but division comes from the grid number. So in this case, 10 by 10. So we are dividing this by 100 in this case. So as a result, you get a value in between 0 to 48, which is this value. So this is correct for calculating the k value. Now I don't want to divide the value with integers, so I'm going to convert this into float and going to get the floor of this result. Now this should be k. Let's check. I'm going to create an attribute called k and check if the value is in between 0 to 48 for each primitive. And we don't see anything. Right. Okay, so it looks correct. We have a value from 0 to 48. That's k. Now, what I want to do next is to separate k into k1 and k2. And by multiplying those two values together, I want to create these value from 0 to 48 somehow. Okay. Now we know that the range of k1 and k2 is n, right? So easy to do. For a k1, we can just say k and calculate the remains by n. The k2, we can divide the k by n and get the floor. Okay, let's check. k1 k2, let's see. So for if the k is equal to 0, 0 multiplied by 0 looks correct. If it's 3, well, if it's 3, this is 3 multiplied by 0. Actually, this should be equal to 1, I guess. No, I think it's correct. You just need to add plus 1 to these k value, I think. Is it? No, I'm wrong. In order to get the value k out of these k1 and k2, what you need to do is to multiply k 2 by n and add it by k1. And if this is equal to k, then that will be great. Let's check. I'm just gonna say temporal kk and check this calculation. Okay, and if the k and kk is the same value, then I'm doing the right thing. All right, looks same. So looks correct. Now I get the k1 and k2. Next, what I want to get is these x1, x2, y1, and y2, which is going to be used for these value here. And if we look at it, x1 coming from the value in between 0 to math pi divided by 2 with the incrementation by dx. So we need to get, in this case, we need to calculate the dx value here which also indicates how many numbers are there for this loop, and which is equal to the division in this case right here. Right? So using this division, somehow we need to calculate the the x1, x2, y1, and y2. Okay. Now let's start by x1 and y1, this one and this one, just coming from this loop, which is in between 0 to math pi. So in order to do that, what I'm going to do is to first of all, what we need to have is the current primitive's x number, an x directional index number, in this case in this direction, I think, starting from 0. If you have 10 divisions, then starts from 0, 0, 1, 2, 3, 4, 5 until 9. And let's say this is the y direction. We also have from 0 to 9. So we do need to know that number in order to calculate these values. Let's call that integer x and integer y. Okay. Now in order to calculate this will be pretty simple to do, I think, since we know how many boxes are there for this setup, and we can pretty much do the same things like I did for the k. Okay, so first of all we have primitive number, then in order to get the x value, what I want to do is to first of all, let me think. I think what I can do is to just get the remains by division. I think this should get the value that I want, which in this case you should get the value in between 0 to 9 in extraction, I hope. Now for the y, I think it's a division. Let's change this to the float. Alright, so let's also check this by having the x attribute and y attribute placed on a primitive. Now in this case I'm going to create a marker to show those attribute. Okay, let's make this bigger. Okay, so for looks correct, starting from 0 from the left side, incremented by 1, ends at 9. In total we have 10 in extraction. Okay, it looks correct. Let's also check the y. Change this to red. Now this seems wrong. Okay. Every y value I do need to make it from 0 to 9, so this seems wrong. Now let's fix that. Now the reason is because there are copies of grid, okay, using this duplicate node. So we do need to consider that as well. So the first thing I do need to do is to get the remains for this primitive by a division multiplied by division. Alright. And as a result, you should get the value in between 0 to 99. Okay, then you could start using the calculations for this one, I think. Let's check. Apply. There you go. From 0 to 9 at y direction. Okay, looks good. Now, now that I have a x and y number value, I should be able to calculate x1, x2, y1, and y2. So I want to create the value with, I want to convert the x value, which is in between 0 to 9, to a 0 to math.pi divided by 2. So you can just use fit function for that. Gonna remap this x, which is currently in between 0 to division, to 0 to pi divided by 2, or multiplied by 0.5. Okay, I think that should do it. Okay, so do the same for the y value. y1 fit y 0 div 0 pi multiplied by 0.5. Or actually, the y range is written like minus pi, starting with minus pi, so I might need to make this minus pi multiplied by 0.5. Later I might need to fix this one later. Okay, syntax error. Where that is. And line 21 right here. Seems I have some error here. Oh, yeah. Okay, so let's consider what the x2 will be, which is, in this code, it says dx plus dx. Now, since this is just a incremented value for the loop, what I just need to do is to reuse this code, but just increment this x by 1. Since this is the integer value incremented by 1 instead of dx, I can just say plus 1. And for the remapping, just use the same range. Let's do the same for the y. Like that. Okay. No errors. Looks good. Okay. So this, by doing this, you have just now created the 4 sets of vector 2 like that, and then feed it into a coordinate in order to get the kind of vector value, the vector 3 value. And later we're going to use these positions to change each quad point position. Now, the main part, we need to implement this coordinate functions. Let's give a space and bring it on the top, and let's try to implement these function right here. Okay, I'm gonna name this function and vector. I want to return the vector value. The let's name this coordinate. And we have these parameters x, y, and the k1, k2, a. So x, y is float, n is integer, k1, k2 is also an integer, and the angle is float. All right. And we already have all those values, so let's try to just implement these functions right here. Now this is where you need to know how you can in order to calculate the complex numbers. Okay. Right here you have in the JavaScript, there's a library to use a complex numbers. So this makes it really simple in JavaScript, but in Vex default we don't really have that. So in order to do the complex calculations, we're going to use an external library for the Vex, which already exists in the installation for this Houdini, and we're going to check that. I'm going to open up the HScript export to see where it is installed and what's the name of it, and we also need to check the syntax of that code. So this is the place where my Vex code is saved, or Vex library is saved. Let's go to that position. Let's go to that folder. All right. Now I'm using it. I'm looking at the Macintosh, but Windows should pretty much have the same folder structures, I think. So it should work both ways. Now let's see where is that thing placed. It is inside. It is inside the folder called include. Not sure where that was. I always forgot. I think it's inside the Vex folder. Yeah, this one. And there is an include folder, right? And these are the bunch of external libraries pre-installed with Vex. And this time I'm going to use this complex.h. Let's open this with a text editor, and you'll be able to see a bunch of code which you can use to calculate the complex numbers in Vex. Okay, in order to use this, we need to include that in a code. So let's do that. Include complex.h. Right. Make sure there is no error. Right. Okay. So in this we have a new struct called complex. So we're going to use this complex structure to calculate all those stuff like multiplication, addition, subtraction, conjugate, absolute, exponential, and so on. Right. What we probably need is in order to construct the complex itself, and also multiplication and the exponential. These are the necessary functions we need to use in this case. Okay, now let's try to do that. So we already have the complex structure. We can call complex. We can as a variable name. And then let's call this Z1. All right, let's create. Okay, so first of all, we are in this case, it is multiplying this result and this result, which corresponds to the equations right here and right here. Okay. Now, the multiplication of two complex is done with this mass.multiply, but for the complex numbers in Vex, we are going to use cmult, which is the multiplication function for a complex number. So cmult, it's going to be called. And you have two parameters, complex A, complex B, which is going to be this one and this one. All right. So let's look at the first line. First, we are creating the complex number right here. And in order to create a complex numbers, we are going to use this constructor here, cmplx. Alright, and then the first value, the real number is 0, so I'm gonna enter 0. The imaginary number is 2 multiplied by path, math.py, multiply k1 divided by n. Just gonna follow that. 2 multiplied by pi multiplied by k1 divided by n. Okay. Now, after that, it is using exponential functions for the result of this complex. So let's check what the exponential for the complex, which is called a cexp. So cexp. So this is the first line. Let's go to the second line. And we have another constructor for the complex. So cmplx, x and y. Then there's and this, as a result of this one, it is used as an angle for this cosine function. Now, you cannot just use cosine as it is for the complex number because cosine only accept float. So we need to know how we can use cosine for a complex number, but unfortunately this does not exist in this library. Okay, so we do need to implement it by ourselves. So for that reason, I have searched for it in the internet, how I can implement this cosine or sine functions for complex numbers, and I have also pasted where I found the equations or code, the pseudo code, in order to realize that in the description page. So if you're interested, please check. Let me go to that place. So this is where I found from the milefoot.com mathematics. It shows some functions, how you can use a trigonometry with complex number, and the one that I need is actually where it is. Where is it? Yeah, this one right here. Okay, so we have cosine and sine applied for a complex numbers, the real number and the imaginary numbers, and this is going to be the actual equations without using imaginary numbers. I mean, it does have imaginaries. This is the result of the complex number from this equations. So let's try to implement this as a function, just like we have right here. So the return, I would like to have a complex, and let's just call this c cos as a in terms of the complex cosine. Okay, and then c cos, what we have is the one complex number. Let's just call a, and or let's call z. Okay, then or c. Okay, c. Let's call this c. Now we need to first of all separate a and b. So I'm going to call the real number and imaginary number like re and I am. So the imaginary number can be calculated like this, right? So cosine c dot, since this is a plus by bi, this is the real number and this is imaginary number, and in order to access those real and imaginary number, we're going to use these term real imag. So the A is the C dot real. Okay. And multiply by cosine H hyperbolic function. And for the angle, that will be C dot imag. Alright, minus, oh, actually this is the real number, okay, for the complex. Now we need to calculate the imaginary number. So sine and C dot real multiply by sine H C dot imag. Okay. Then finally we can return the complex number combining this real and imaginary number together. Okay, syntax error again. Let me see where it is. 12. Okay. I should make this commented out for now. Okay, let's check this later. Now we also want to get the sign, so let's copy this one. Call this C sign. Input the complex number and I'm going to change the function. So starting with the sine C dot real and cosine H C dot imag, this is the same, and this one is, okay, actually this has to be negative, and this one is cosine C dot real sine H B. Okay. So this should be the trigonometry functions for complex numbers. So let's try to use this. So we'll go back to the function, and we were using right here for this one. So C cos. All right. Now, next we have a power functions. Now, unfortunately, again, we don't have that functions again in this library. So we also need to implement this power functions for the complex number as well. And let's do this. I'm gonna comment this out again. And unfortunately, that didn't exist in this page, so I needed to search for it again. And I found one page which seems to have that implementation using several code. I have also pasted the link to the video description page of this live, so if you're interested, please check at the Geeks for Geeks webpage, Programming for Power of Complex Numbers. And inside this tab, you can just choose whichever code you want. Yeah, probably I could just use C++ or Java, or anything is fine. Just want to use the most readable code. Let's just use Python. Should be the easiest to check. Okay, something really, I'm not sure if we have this for Vex. Do we? If we look at the C++, not sure. Oh well, let's try to do this. Okay. Or maybe Java or C#. It's using long. What's long? I guess this is the complex number. Or this thing is like a sequence. Yeah, I'm just gonna look at the Python and try to implement that function. cpal complex C1 complex C2 no, actually this last one should be float value. Yeah, right. Okay, and let me see. First of all, it's creating a array including 0 multiplied by 2. Huh. Not really sure what is it really doing here. Okay, if it's checking if n is equal to 0, then it is returning the 0 as a return. So this should be the complex number for the returning. Alright. Now I don't think I need this conditions for myself, so I'm just gonna skip it. If it's equal to 1, return x. Maybe I can include that. So if n is equal to 1, then return CMPLX. No, I mean you can just return the C1 as it is, or just C. Well, maybe I can also implement this as well, just in case. Maybe I can reuse it for something else later. So if n is equal to 0, then return the CMPLX 0, 0. Alright. Now this is the main part. First of all, it's calculating the square for the x value. Wait a minute. Where does this x come from? Power. Where does this power? So it's calling this recursively, which I cannot do that in Vex. Okay, I gotta skip this one. What about Java? Is it all calling recursively? Yeah, it is. Okay, then I realize I cannot use these code. I mean, I probably can use a for loop to implement similar stuff, but not a good idea. Okay, I'm gonna look for something else, which I did for the sample code. One thing is that I forgot the reference. Let me search for it. Yeah, it was using trigonometry with the power. And well, hopefully I'll be able to find where I haven't picked up the function. Nope, it's not. Okay, there you go. This is it. I'm going to paste this to the video description page just in case I can, so that I can refer to it later. What's the name? Okay, I'm gonna copy this as a title. Okay, just save to the video description page, and you have the power, I think, which is this one. Okay, I think I can use it. Now, first of all, it's calculating something called mod. So I think I should start from this one, mod, right here. Okay. Is it a modulus? I am not sure. And it returns, what does it return? It just returned a float. So mod, and using complex number. Okay. Return square root and c dot real power of 2 plus again power of 2 for c dot imaginary. Alright, now we can go to the power function. Okay, I'm just gonna remove this one. First of all, get the mod. And this is the actual complex numbers that I need to return. So return CMPLX. Okay, so power of mod by P. P is, in this case, I'm just gonna replace the same value, P. Okay, multiply by math.cosine. Cosine, inside a cosine will be P multiplied by arg. Okay, another unknown value. Okay, and power of mod by P multiplied by sine, P multiplied by arg. So what does arg? What is arg? Okay, here it is. Arg is math.acos self real. Okay. Just going to create another float function. Call arg. And that will be, we need to have a complex number as an input, then calculate acos c dot real c dot mod c, like that, and this should become arg, and I'm going to call it like function. Alright, so I think I have some errors, so let's check. No matching functions for float acos. Float. What did I do wrong? Okay, I think I shouldn't use comma, but it should be division. Alright, no errors. So now I am ready to go forward for these calculation. It's long. Takes a long time because Vex itself doesn't have a default functions for the complex numbers, so that's the reason. But I think I have enough now. Now this is where I left off. See POW. And this one with 2 divided by n. And I think I should bring all those functions above, because Vex reads from top to bottom, even for the function. Okay, no errors. So hopefully this went well for the first Z1 complex number, which corresponds to this one. Or I mean this one. Yeah. Okay. Next, Z2. Z2. It's a lot of calculations, but sometimes you gotta do it. Okay, so pretty much the same, so I'm just going to copy these and change some of the value. So the first line looks pretty much the same, only this one. Okay, 2. Now the second line becomes C sine, complex sine. Alright, and there you go. Okay, now we have 2 z value. We are ready to create the vector 3 coordinate. Now instead of using 3 dot vector 3, we have Vex have vector 3 as a structure. So I'm going to use set z1 dot real, z2 dot real, and z1 dot imag multiplied by cosine of a plus z2 dot imag multiplied by sine of a. I think this represents the rotation in one axis, in this case the axis, right? I mean, maybe not, I'm not sure. Okay, hopefully this is correct. Now I think I am ready to use this coordinate functions right here, which I have left it here. No errors. Okay, it's time to access the point numbers in primitive and change those point positions. In order to do that, we need to access to each of the quads point numbers using prim points like that. Okay, now, and fortunately the order of the points from the primitive number is, I think, is a clockwise or counterclockwise, I think. If not, we will change it to the prim vertices. Let's check, let's see. Set point attriv 0 p at ptsi with this new positions, and if you to remove the marker, you see something that doesn't really look like this, but something similar. Okay, let's change let's set the value to the same value. So projection to 0, exponent to maybe 3, and do the same for this one in Houdini to see what's still missing. 3 and projection to 0. Okay, so This one looks like this. Now in Houdini, this one looks like this. It's kind of a missing a half of the piece somehow. And I found out that by using a mirror to this half size, using direction for Z, you get something similar. I think the same thing if you look from this way, right? So somehow it's missing a half of the piece by implementing the same code. And I thought about those ranges, but I'm using the same range right here. Okay, so I couldn't really figure out where I did wrong. I am assuming it should be related to something like here. I mean, there were so many ways to calculate power of complex numbers. Maybe this is somehow wrong, or maybe something is wrong at some point. But the result, I could get the result by just using the mirror, so it's kind of a I don't really like that there are some questions left over, but as a result it should be fine. But instead of using mirror, I just want to do this all in one code right here instead of having a half part of the geometry. So in order to do this just by using this code, I do need to know how I can create the other side of the geometry, just like this mirrored result. Okay, so if we look at the part where it creating the z coordinate, it is coming from this one right here. Okay, and I found out that by multiplying this z value by -1, you get the other way, you get the other side. Okay, so it seems like if I can loop over the two grid, one for the positive z value and one for the negative z value, then I can just get the same result, just as I did for the mirror. Okay, so what I want to do is to include another loop, which is the iteration of two, one for +1, one for -1, to be multiplied right here. Okay, in order to do that, I do need to have another set of grid to this one. And another mysterious thing that I have is, by keeping the code as it is for now, I get the half size of the geometry, but seems like there are two overlaid quad in the same positions. So if I remove one of the grid like this, I still have one left. So in the same position, I have two quad with the same point positions. So definitely something should be wrong with this calculations. By using this -pi 0.5 to -pi multiplied 0.5 should give me the other side, but somehow it didn't. Okay, and that might be due to the calculations right here. This is the imaginary for the complex z1 and z2, which is using right here. So somehow it should give me a negative value when the x and y is equal to negative, but it didn't. So maybe the complex cosine is something wrong, or complex power is something wrong. I'm not sure where, but it must be it. So it's not really complete. It's not really complete. I mean, I have checked over and over again if I have implemented correctly, but it seems correct if I have just looked into those. Not this one, or the power functions. The power function seems more complex, so maybe this is where it gives me the wrong result, maybe. But I am not really sure for that. Yeah. So if anybody know how I can resolve this problem, that will be great. Keep the comments on the video, that will be great. But for now, I couldn't figure it out, so instead of just solving these part, I'm just gonna try to create another loop to brute forcefully implement the negative z value for this one. Alright, so to do that, first of all, I can change the range for the y. Right now it comes from negative pi multiplied by 0.5, but I can just set this to 0 just as I did for the x. And as a result, what you get is just the one side of the geometry, which is totally fine. Okay. So from here, in order to add another side of the grid, what I'm going to do is to increase the duplicated number by multiplying this by 2, because the number of the grid will be doubled, because you're going to create the half side at the other side. Right. Now after you did this, what you need to do now is to go back to the code and consider this additional value to be used as another integer value, and I'm gonna call this as t, or if I'm not using anywhere. Okay, so let's call it t, and to get the t value, I either want 0 or 1 from the primitive number. Okay, so to do this, I do need to give another calculations to get this t value, just like I did for x, y, or k. So let's try to think how I can get that. So first of all, the total number of grid before multiplying by 2 was the exponent value multiplied by the same exponent value multiplied by the division multiplied by division. Okay, so going back to t, first of all, I am going to divide the primitive number by division multiply by division, and wait, that's that is equal to the one number of grid, and then multiply by the n, multiply by n, and give it a float and give it a floor and check if t is in between 0 and 1. Let's see. So we have 0 and 1. So hopefully this can be used inside the coordinate calculation. So I'm gonna add additional t parameter for the coordinate. Right here. Right here. Okay. And want to calculate, I want to multiply +1 or -1 to this z coordinate right here. So let's try to have the value. M is equal to t. If t is equal to 0, then you get -1. Otherwise 1. Then multiply it to this. There you go. Now I have just mirrored the surface to the other side. Now the direction is opposite, so maybe if you want to fix that, I think I should do something more to this. What can I do for this? Let me think. I'm not sure. If I multiply an angle, nope, didn't work. I think there is a way to fix this direction. Direction comes from this order here. So what I just need to do is to change the order based on the t value. Alright. So how do I reverse the order in Vex? Forgot. But if t is equal to 1, then reverse data. Didn't work. This will return, okay, so I gotta say data is equal to reverse data. Nope, didn't work. Give me something weird. Okay, shouldn't do this. Let me check what I did last time to fix that. Okay, I think what I did is instead of multiplying t or a negative value to this one right here, what I did is adding angle by pi multiplied by t. Well, it gave me the same result, but didn't really fix the upside down problem. Did it? Let me see. Let me check. Well, if I cannot fix that, then I'm okay with it. But let's see. I wanna know what I did wrong, at least. Okay, so if it's based on the angle like that, I mean, just multiply -1 is the same, but probably I could modify these value here. What if so before we have -pi right here. And in those cases, we have a other side normal direction. So if we can flip that based on the t value, then we could get the normal direction fixed. So I'm just going to subtract this by pi multiplied by t. So if t is equal to 1, you get -pi multiplied by 0.5 to 0. And I should divide this by 2 or multiply by 0.5. Nope. Huh. The other side just gone. How's that? Well, I realize I shouldn't do this inside a fit, but I should do this outside a fit function. Just like that. Okay. Now I think I have what I want. Now it's totally doable with using mirror, but just my preference. I don't want to add any node to it. Okay, looks good. And the good thing about this is that process pretty fast since I'm using primitive wrangle. And the result that I get is something like this. Pretty interesting. Alright. Let's try to visualize this with a matcap. I have a custom matcap, so let's try to use that. Okay, looks like this. Alright. Looks good. Now going back to the smooth shaded. So this is pretty much it in order to implement the Calabi-Yau manifolds using Vex. Most of the calculation is done using complex numbers. As you can see, in order to use complex numbers in Vex, you do need to implement your custom functions for complex numbers, including the one from the Houdini's pre-installed ones. But it does seem to create the things that I wanted, just as it shows in this website. Okay. Now, since I'm using Houdini, there should be more extensions to this one. I mean, since this is a surface, I could probably use it for other purposes after I have created this shape. If not that, then that'll be boring. So let's think about how I can use this for other purposes. I mean, I don't really need to have a purpose, but let's see how I can reuse this for something else to create a bit more interesting geometry out of this. Now, one thing I could think of is to use a UV mapping to this. And in order to do that, you do need to have a UV on top of the surface. But since I have started from the grid, if I have attached a UV to this one and I'm just changing the point positions of this grid, then I should be able to preserve the original UV. Let's see, UV texture. Now I have this map, and going to the result, I can see now that the UV map has been cleanly distributed over this surface. Since it already started from the grid, you have no problem distributing onto a 3D surface like this, which makes it which opens up a really vast possibilities how you can use this surface with. For example, you can map your own like bumping on top of the surface with these UV mapping. Let me try. So for example, let's have this as a reference. Okay, let's show up the grid. Hello everybody, thanks for the comment. Can I ask you about the Houdini and the hardware? Yes, if you have any questions, please do. Okay, so what I would like to do here is to create some bumping effect or wave effect to the surface to make the final geometry having some textures or surface textures. The easiest way I could think of is to use the sine or cosine trigonometry based functions. Okay, let's call this wave, and actually this is a reference, so this should go to the second input, and what I would like to modify is this surface itself. Okay, and let's also create the UV as a point attribute, since I want to use it inside a point wrangle. Okay, now I can refer to the point position or any kind of attributes applied to the grid using UV sample. Function like that. So let's try to use this. I'm gonna call this mapping, and I am going to apply another wrangle in between this one to modify the shape of the original grid, or apply some attribute values to it. For example, changing the height of this grid using the trigonometry, like cosine on x direction and y direction. So let's get the bounding box information first of all. Then get the x angle by remapping the x value, which is in between x to max x, and change this to an angle based value. Maybe if you want to make it continuous, the multiplication of 2 pi. Same for the y. Now in this case, this is on top of the z axis, so probably this will be z. Okay, same. Now I can now use cosine, add 2 cosine values together for the height. Alright, this is one wave, and if I can implement the parameter to control the wave number, let's just call this W. I can now increase the number of waves like that. Okay, and let's try to get that information using this UV sample right here, and this will give you the informations of the height of this grid. You can get the height information by accessing to the Y from the second input, and then you can then move your point, the original point got here. Let me reset to the normal direction of the surface. Now I don't think I have the normal attached to this yet, so let's give it using normal node like that. Okay, and then I want to move the point to the normal direction by this height information got from the UV sample, and multiply by some weight, how much height you want to apply. There you go. And now the Calabi-Yau shape has been modified using additional like surface modification using UV. And now this is out of like mathematical definitions whatsoever, but this is just to play out with the shape that you got out from the equations, which is easy to do because you're using Houdini. And that's what's best about this tool. Alright. If you want to make something really interesting like shape out of a uniform equations, there are so many ways you can do with Houdini. Right. And what else? Let's try with the noise function. Periodical noise might be interesting. So let's see how I can use that. Forgot how to use that P noise. Okay. So P noise is being used. I think I just need a 2D vector value as an input, so this should do it, I think. And px and py is the periodic number. More you have, more variation you get. Okay, let's try to use that. Okay, I'm almost done, so if you have any questions or feedback, let me know. If not, thanks for watching. Have a good day. Okay, so let's try to implement this. P noise based on the X and Y value. Now, I don't know the range for the X and Y, so I'm gonna use the same method or technique. to first of all fit that x and y onto the range px and py. So first of all, I need to define the px and py. I'm gonna call this r, starting with some numbers like 3. Okay, then so first of all, I would like to map the x and y into in between 0 to 3, this value. So float x is equal to fit min x max x 0 to r. Y or z is equal to fit z min z max z 0 r. Alright, now x and z and 3 and 3. Okay, and let's try to use this as a height to see how it looks like. Okay, well, maybe I can increase this a little bit more. And yeah, it looks like that. Maybe I can make this as a parameter like r and see how it's going to change stuff. Okay, so what's good about this is that it is continuous, left and right, top and bottom. And because this is continuous, it is also looks continuous in the Calabi-Yau manifolds. Now this is the wave pattern, but this is the noise pattern. Well, I guess I'm wrong. This is not continuous. It is continuous in one way, or is it? Maybe not. Okay. Unfortunately, this was not really usable. Okay. Is it continuous? This is continuous, but the way it's aligned, the way grid is aligned was not as I expected. Seems like. So the cosine wave went okay. This one didn't really go well. Yeah. Let me see how it looks like with the small number of. Okay. So this is the half. This has been mirrored. Okay, so I guess this part and this part must have the same shape, which is not, which doesn't have it right now. Okay, understood. And I'm not sure if I can use B noise to create that kind of stuff. Probably I could. I just need to rotate it. Yeah, rotate the well, how did I thought, well, let's forget about it. I'm going to skip using noise. I'll think about this later. I'm just gonna keep the wave pattern and just try to increase the number of parameters that I can control for this wave, like the number of wave, the height. Yes, pretty much it. Guess that's pretty much it. Yeah. Okay. Well, if there's no any other questions, then I would like to end the tutorial live for today. Thanks for the late note. Sorry for the late notice. I didn't have much time to prepare for this time, so the topic that I chose was pretty simple in terms of the implementation. Just takes time because of the complex numbers, but that's pretty much it. Okay, let me just drag and drop these values. And if you are still here, let me know if there's any things that you'd be interested to see created in Houdini. That would be great. Okay, so this is wave number. And this is the wave height. Well, assuming everybody has just been left, I think I'm gonna try to look for something interesting that I can use this UV for. Let me think what I can do with these. What about running some like continuous ball on top of this grid? That might be interesting. And see how the ball moves. Alright, to do that, what I need is the point wrangle, or I'm going to create a scatter node on top of the surface. Just give a small number of points being created, like 3. Alright. Now what I realized is that this side and this side should have the same shape. So when the ball goes out, then it should come out from this point. If this is come out from here, go out from here, then it should come out from here, I think. That's kind of a strange result, but that's what it should look like, I think. Let me see, let me check that. I'm gonna check it by just having 1 point. Copy the sphere to that point. Right. And show up how it looks like as a reference. No, I don't really need a way for this one. Okay. Now, so this looks like this, and I want to refer to this point position on a grid. So to do that, this is one type. I'm going to create another type for a mapping. Mapping ball. I should refer to the reference plane as well as this point position here. Okay. So first of all, what I need to get is the corresponding UV for this point on top of this grid, then use that UV value to get the point position on top of the surface. Okay, so you do need to use two UV sample functions. First of all, you do need to get the reference UV from the second input using the point as a UV. And the point itself comes from this scatter point. So point 0 position, and then I can get the surface point positions on top of the current surface using UV coming from the grid. Alright, then create the new point to that surface point position. Let's set the color to that point, something visible like red, and then set some group. How do I call this? Ball. Okay, set. Alright, and did it appear anywhere? Not sure. I'm not sure, so I'm going to use the copy to SOP to visualize it. Oops, I don't want to use every point, so just want to use the... Okay, it doesn't really exist. So actually, I really shouldn't do this with the point wrangle, but instead I should do this in detail. And I also think I don't really need the first input, so just get value from the fourth input like that, and it does create 1 point. Well, where is it? Actually, the problem with this is that I have so many similar UVs from this surface, so I cannot really do this way. Yeah, I realize. Okay. Now that seems like a challenge. Right. Right. But still, where is this point? Okay, there you go. But actually the number of points that I need is the number of grid that I have, which is being duplicated with this copy. So to do that, I do need to modify the UV value as well. Now, that's a lot to do. It's a lot to do. Okay. Going to the copy to duplicated node and check the copy number so that you know which primitive belongs to which grid. Okay, if you're already satisfied with the Calabi-Yau, then you don't really need to watch the things that I'm gonna do next. Just experimenting. Okay. So with this info, what I'm gonna do is to try to modify the UV value that I've created right here, so that each plane has different UVs. Right. So I'm gonna do that by using point wrangle to access the UV. Okay. And also get the primitive number. Then use that to get the copy number. Then use this to modify the UV. So UV copy number multiplied by, I don't know, 10 is enough, I guess, for X and Y. Now each grid have a different UV value. Doesn't look like so. Okay, okay, I should do this after this one. Okay, looks good. Alright. Now using these infos, I can now create a loop. Let's say if I want to, if I have 3 points, then I'm going to create a point wrangle for these points. Ouch. Right. I could just do it in one detail, but as I said, it's not an efficient way to do this. Assuming I'm going to increase this number really big later, but for now, I'm gonna try with really small numbers. Now, with the 3 points, what I need to do now is to access each UVs on each grid. So I'm gonna use this one as a reference, and also I should have this one, the base grid, as another reference. Anything else? Nope, I don't think so. Alright, let's rewrite. Okay, so I'm gonna copy these to here, and so I have right now the current point position, so I can skip it, and I can get the UV value from this third input, like this, but using the current point position. Right. Now, yeah, should be fine. Now I would like to have an information how many grids that I have. Meaning how many duplicates I did. I'm just gonna copy this parameter here and have it referenced right here. Alright. Now, what I'm gonna do is to modify this UV based on this grid number, just like I did right here. Multiplication of 10 by the copy number, which represents the grid number. So I'll do this with the for loop from 0 to the grid number. Now I don't really want to use for loop as much as possible, but in this case 40 or 50 number of loops, it's not that large, so I'll go with it. Okay, so where was I? Going to modify the UV by the same calculation I did. The UV10 multiplied by I for X and Y. Alright. Okay. Now inside this loop, I would like to get the new point position. Looking at the first input, second input with this corresponding ID, I mean UV, and to do that, I need to have that modified UV being used right here. Like this. Yeah, I think it's correct. Is it? No. Actually, I should bring this one to the reference. Okay. Now this might kill the wave function, so let me fix that. Okay, getting complex. Okay, as I assumed, this killed the wave functions because it's using this different UV value. So before using the mapping function like this, I need to refix the UV for this wave function. Which is easy. You can just use a modulus with 1 for X, Y, and Z, which should fix the value in between 0 to 1, like this. Okay. Well, it didn't really fix the edges. Right. Because you don't really get 1 if you calculate the remains with 1. I see. then this is not a great fix. Now, in those case, I'm just going to subtract the same number I have added. Copy number. Okay, then 10 multiplied by copy number. How's that? All right. Now that's good for the wave. Guess I gotta make it as a group. Okay. And what I wanted to do is, after I have calculated the current point position on the surface, I'm going to add it as a new point, set the color and the group. Now, did it work? Where is the ball? I think I'm not seeing any balls here. There are points. Ball is not valid group. Oh, okay. I don't really need this target. But okay, this has to be group. Okay, this is too big. Okay, let's merge it with the original surface and see how it looks like. I wonder why it is not on top of the first surface. And okay, that is because I have this wave function somehow being kept. And it looks so weird. Okay, I think I didn't really fix it. Okay, looks very weird. Or is this just a cache? Nope. I think I did something really wrong. All right. Okay, what did I do wrong here? Okay. Did I really fix the UV? No. No. Doesn't look like so. There are numbers which is more than 1, so that's a problem. For sure. Do I have this copy number? Yeah, I do. Yep. And the maximum UV value, that I have here was okay 49. So not really sure what and went wrong with this one. Okay. Okay, well, there is no extra sign. Oh, did I forgot somewhere? Where is that sign? There is no extra sign. Wait, am I missing something? So this is getting the copy number right. And I'm just reverse engineering like that. Just subtracting. I was hoping to get the value from 0 to 1. No, but I didn't. How? Why is that? Wait a minute. Oh wait. Now this looks correct. Huh. Maybe I was having a problem mapping the copy number. Okay, so but I don't really need the wave number, I just wanted to fix it. Okay, what I want to try out is these points. Now these points should correspond to the point positions which is on the grid. And I want to know if that's true. Okay. So the size is a bit different. So let's try to make this big enough. So we have 3 points like this on a grid, and inside on top of the surface looks like these. Not sure if it corresponds correctly, so I'm gonna limit the size of points to 1. And what I'm going to do is to show up the grid. Oops. Show up the grid like that and move the move this point position on a grid to see if the surface, the ball on the surface also moves. Okay. Okay. So let's try to move the ball. Okay, as you can see, the ball is moving on a surface. If I move this on a grid, and what I want to check out is if I move those points. Okay, where did it go? it is not moving. Okay. What I want to check out is where does this ball comes out when it goes this way? It's this way. So this side corresponds to where? Is here? No. Obviously not. So is it here? Doesn't seem so. Is this one here? No. Is this one here? Huh. It's getting confusing. So if this is right here, I want to have the ball appeared from here somewhere. If it's touches here, or if it touches here. Nope. Okay, am I thinking something differently? So it's moving like these. I think I'm not getting all the points that I need, is it? I don't think so. I think I'm missing the grid, the point positions for this grid. Yeah. I think that's why. So I have 51 points. If this is this correct? 50 points. Wait a minute. That doesn't sound correct. This is 50. This is 50. Why do I have only 50 points? No, that's wait, but that's correct. Yeah, that actually that is correct. I just want to remove the original point. Okay, let me try to place as much. Okay, now I can see that some surface is missing the ball. Right here, the other side. So that's why. The reason, the number of grid should be correct. So probably due to the UV sampling. That must be the reason. Okay. Let me check the UV again. So, like that. And Let me check this UV. TUV, TUV, TUV. 0. What? Okay, so that's what's wrong. Let's limit this to 1. And when I move the point, this TUV... wait a minute. Actually, I should have comment these out. Okay, so I do have TUV and showing up the grid. Okay, but I am changing the point position. But UV is not changing, or TUV is not changing. Oh wait, it is changing. So 0 to 1, that's good. 0 to 1, okay. So that's good, so that's good. Okay. So this part is okay. Now what about the part right here? Right, how do we check this? I'm going to apply a UV to this newly created point. See how it looks like. Wait a minute. I shouldn't do this. I should create it as a new variable. Maybe that was the reason. How's this? It says it's 50 points has been created, but I don't see it. I don't see it. That is because... Okay. Alright, that looks more promising. Now, if I change the point position on the grid... Okay, so... Let's see. So when the point is on this edge, I don't know how I can connect it. If I go move this way, so this pretty much goes to the same positions as I assumed this one. This position and this position is not the same. Okay, let me remember where it is right now. So if the point is right here, this point is right here. Now if I move this to here, nope, here. Okay, so now this is at the same positions. So this, if I change this to 1 here, right here. Okay, so well, I don't. Now this one seems not connected. Interesting. So if the z side can be go through from one side to the another, but the x side is actually not connected. Interesting. So I am assuming if this is right here, this comes right here. Is it? No. No, actually not. If this is right here, okay. This is right here. Actually, this is, so looks like it's bouncing from this to this. You have a curve like, wow, that is pretty interesting, the connection. So if the ball goes out from here, then it comes out from here. Goes out from here, comes out from here. Ah, I get it. Weird, but interesting. So this is how it's being connected. Now, using those informations, I would like to create the ball running on top of this surface somehow. Right? Now, I don't think I can use the point wrangle as it is, so I'm just going to try to use a solver to solve it, the bouncing problem or the border problem. Okay, so enough with the editing. Let's try with just 1 point for now. Okay. And what I want to do is to move this point before mapping onto the surface using solver. It's getting complex. Okay, now I can just move it to any direction I want. Maybe just using some noise related value is fine. But let's try with the like straight directional movement for now. I'm going to create the attribute create. With the name velocity. Point vector and the default value to some random direction. Okay, so let's use those velocity value for the point to move into that direction inside a solver. You never use attribute bop, only wrangle. Bop, no, I don't use bop. Because it takes more time to use bop for me. Because you need to remember the name of the bop node. It's much easier to remember the text-wise code name for myself. And connecting like those node with a lot of wires takes a lot of time for me. So if you can use Vex, then I think that will be much faster to implement. Not in terms of the speed of the process, but for myself to write the code. The Bob itself runs really fast, I think. Where was I? Move. So I just want to move the point to that velocity direction. Let's normalize it with some kind of speed. How much speed do I need? Not sure. 0.4, 0.5. Okay, and the important part is to set the boundary conditions. So let's connect the boundary, which is this grid. Right. Connect that information and get the bounding box information. All right. Now, as we saw, if the z in the z direction, the ball can go from one side to the another from the other side. So if at p dot z goes over the max dot z, then it can come out from minimum z. Pretty simple. Same for the other direction. If z is minimum less than minimum z, then it can come out from max z. Now for the x direction, it gets a bit more complex. If at p dot x is more than max dot x, then it comes out from the same x coordinate but different z coordinate. How weird is that? Now it comes from the negative z value, and the velocity should be going to the other side, other direction. So I'm going to multiply the velocity to -1 as well. Is that correct? Yeah, I think so. And same for the other x direction. X is less than minimum. Then you should multiply z by -1 and velocity -1. And let's see how it does. Let's see how it goes. I'm gonna check it out by visualizing on top of the grid first. Play. Whoa. Whoa. Where'd it go? Why did it? Oh, wow. Did I change y value? Seems like I did. Seems like I did. Why? Why did it go to the... Oh, okay, this one. Okay, I should limit the y velocity value just in case to 0. Okay, let's check. Interesting movement. I want to change the direction. Ba, 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 ba. Okay, and hopefully this movement will create a continuous move on top of the surface. Let's see. At some point it goes really fast. Maybe the reflection, the direction is wrong for the Z part or the X part. This one, I shouldn't just multiply by 1, but I should create the reflection for this one. Right, so let me think. So comes from here, so I just need to multiply the X value to -1. Let's see how it goes. No, looks more weird. Or is it correct? I don't know. I should make the situations a bit more loose. I don't want to have this point starts from somewhere on here, but let's change the initial positions to somewhere close to, yeah, somewhere around here. Okay, and I'm gonna show up both so that I can refer to the grid as well. Let's see. Now this is reflecting. Maybe not. Maybe I didn't really want it to reflect it. Maybe the one that I had was okay. It looks still continuous, so I guess that's fine. What if I increase the number of points to, I don't know, 5, 6? It's gonna be really busy. When it gets close to the center, it goes really fast. Well, that's understandable because you have kind of a modified UV. But as you can see, everything is kind of a continuous, so probably that's okay. The ball's moving. Now starting to look like a bug. Let's limit the number of points. Try to make the movement a bit more randomish. Shall we? Going inside here. Instead of using G attribute create, I'm gonna create the random velocity. as an initial value. And inside here, limit the y for the velocity to 0, that's fine. And let's see if I change the initial velocity to something randomish. It's gonna become something interesting. Now when this one goes outside, it seems to go outside, come out from here. Now, which is understandable because there is no connections to this edge. So, but thing is that I do want, in those edge reflection, I want to just bounce off the edge. Going to the other way is fine. Huh. Oh well. In those case, maybe I don't really need to change the position. Just bounce the velocity. Nope, didn't work. Oops. Pop. Wait a minute. Do I need to use this? If it's just bouncing, I think so. It's moving too fast somehow. That is because it's changing the position. So, somehow I gotta copy this here. Reset the positions. Before it goes over. No. Nah. Doesn't go well. Let me change this to 1 and see. Okay, so the ball corresponds to wait a minute. Okay, well actually this one was okay. I didn't really need it to change it. Wait a minute, this looks not correct. Oh, yeah. Okay, so this is okay. Now this is where it goes wrong. So if it goes from bottom to top, doesn't go okay. If it goes to array, but I don't think I can do thing for it because the inside part looks okay, so or I can just implement the reflections for these for the velocity. How's that? Yeah. Like that. How's that? Better. Now I don't want to move to the same direction, so just going to change the X, or is it? Think so. No. No. Z. Better. All right. Now it looks more clean. Now I don't know what I'm expecting out of this. Just looks interesting. That's all. Interesting, right? Even with the 1 points on a surface. Hope you found this interesting. I mean, I do enjoy it. How the ball moves on top of the surface based on the movement on the grid. Alright. You can also add the wave if you want. Wow. It's kind of a rusty. Well, if you are good enough, you'll be able to collaborate these wave together with those point movement. That might also be interesting. Alright, I think I am good with it. I'm going to go sleep now. Let me change the math cap again. Okay, so that's pretty much it. If there's no any other questions, I am going to end this live tutorial. Thank you for watching. As always, really appreciate it. Hopefully you have found this interesting. I am going to upload the files to the GitHub and paste a link to the video description page of this video so that you can download to see how I implement it, the same file that I have created today. And I'm also going to upload the files to the Patreon page, which you can download for free as well. So, and if anybody likes these kind of tutorial lives or things that I make, if you could support me on Patreon, that will be also great. Okay, that's it. Thank you very much and good night, and have a nice day.